So these arrows represent the velocity and direction of water flow along a smooth or solid surface. So what you can see is that the direction of water is the same for everything, but you close to the surface of the water, you have slowed down because of friction with the water and the surface. And then it gets faster and faster in this area of what's called laminar flow. Laminar meaning like a sheet, like a layer. And then at the top here, you get what's called turbulent flow. The flows start to become more turbulent. Okay, so as you have zero velocity, you're increasing water velocity as you increase the distance from the surface. And then at some point you end up past the flow boundary layer and you get that turbulent flow. So these are just some images to help you understand. This stuff is pretty difficult. A lot of it is fluid dynamics and physics. We're just trying to kind of understand it at a medium level. So we don't need to dig into the details too much, and we'll practice using some of these equations in workshop. So here's another example. This shows you kind of a rough substrate and the flow boundary layer, okay, where you have really slow flows along the surface and then you have faster flows outside of the boundary layer, okay. The thickness of the boundary layer increases with distance from the leading edge, and it's shallower over bumps and deeper over depressions. So you can imagine as an organism, you might want to like tuck down in some of these depressions, right? And so a lot of organisms have adaptations to getting out of the swiftest flow by pressing themselves to the surface of rocks and hiding in crooks and crannies. All right, and then turbulent flow. If we have the direction of flow going this way in this figure, we can see that different shaped objects at different Reynolds numbers create different flow conditions downstream. So at very low Reynolds numbers, all flow is laminar. So this is slow flow, right? And then if you increase your Reynolds numbers, but you're a square box, you'll start creating vortices, okay? And then eventually you'll get this turbulent flow if you get swift enough movement. But if you streamline your body, then you can create laminar flow conditions at much higher Reynolds values. And so this is why streamlined bodies for larger organisms like salmon are common adaptations. And so you don't ever get this fully turbulent flow. You start creating vortices behind you at this high value of Reynolds number. And so this really helps organisms to avoid the disturbance of turbulence around them. Here's just a picture actually showing images from a flow chamber. Okay, so you can see as the flows increase that you increase this turbulence at different velocities. So over time and through space, we get different types of flows. Okay, and so this shows how water movement is related to both temporal and spatial scales. So small spatial scales over short periods of time, we just get like molecules moving, right? And then over small distances and small times, like a second, we might get laminar flow, right? Shh, 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 shh. But if we move to larger distances or larger periods of time, we get turbulent flow. And then at the greatest scales, we're talking about like the whole hydrologic cycle, okay? And there are a lot of really cool adaptations to flow that organisms have. This shows you a Blepharoisidae larva, which is a type of a fly larva, and it has these little suction cups on its belly that help it to stick down to the surface of a rock. And they're very cute. This was a picture that some of my students took in the microscopy lab a few years ago. So lots of really cool adaptations that we'll talk about. This just shows you, this is a nice figure from the book that shows you if you're a small organism, you're likely dealing with small Reynolds numbers. If you're a large organism, you're dealing with high Reynolds numbers. And the differences between viscous and inertial forces on you, okay? So viscosity is more important for small organisms, but inertia is more important for large organisms. Most likely dealing with laminar flow if you're small, but turbulent flow if you're large. You're most likely streamlined if you're large. and we'll talk more about diffusion in the future. And if you're a particle, it's going to be faster for you to fall out of the water than if you're small. And you're going to require more energy to move if you're small than if you're large. So some of these things seem a little counterintuitive, so it might make sense to spend some time thinking about these things. All right, how do you measure flow? We're going to do a variety of things, but everyone's going to get a chance to use a neutrally buoyant object like this tangerine to measure flow. And basically you put an object that floats but not on the surface but kind of sinks a little bit in the stream, and you measure the amount of time it takes to travel a certain distance. So that's velocity. It's a distance over time, miles per hour, right? That's a velocity. There are other ways to measure flow in larger streams. You can use propeller-based flow meters like swaffer meters. You can use dyes. We're not going to do this because it's a little damaging, but it's pretty cool to look at pictures of. And then you have these magnetic flow meters. I have one of these, but I'm not sure that everyone will be able to use it, but I can bring it out to show people. And then you can see how you need to move along and measure flow at different, along a transect of the stream to understand how fast the water is moving overall. And that's the first lecture. Great job, everybody. I hope you take breaks as you go through these, and let's move on to the next one.